Okay, folks, we have Tim Ruppel from Perkin-Elmer on the line. Tim, can you hear us? I heard you a moment ago.
What's that?
I was just checking to see if you can hear us.
Yes, I can hear you just fine.
Oh, welcome. All right, we've got a room packed full of people ready to hear your presentation, so I'll give it up to you. Thanks, Tim Ruppel from Perkin-Elmer for giving us a presentation tonight.
Okay, I was asked to give a short bio on myself before we got started. Let's see if we know how to advance this thing. I have been with the Perkin-Elmer Corporation for the past about 28 and a half years or so. I hail out of Michigan State University and Purdue University, so I'm all Big Ten myself. I spent 15 years right out of school in the law enforcement community. I worked everything from uniform patrol to homicide, crime scene investigation, technical narcotics teams, drugs and toxicology. I worked in forensic laboratories for police departments for about 10 years or so. On everything from the city, county, state, federal, and international levels. And I'm probably one of the few people in the industry now who has the infamous claim to having put more than 100,000 people in jail for this product now. And look where it takes us now. Now we are legitimate, we're getting legalized, and now we move on to a new application for cannabis. So with that, we're going to talk about a few of the different types of analyses that are done in cannabis laboratories. Some being contaminants, adulterants. You wouldn't believe the number of different types of things I've seen in diluting cannabis, including things like sand and powdered lead, using microscopy to make sure it is indeed the correct species of plant, looking at moisture content. Potency is the biggest area for the cannabis laboratory analysis. Pesticides and microbiological, in order to make certain that everything is safe for the user. These are never done on the clandestine samples. Likewise with the heavy metals. Tonight we're going to concentrate more on terpenes, but residual solvents are yet another analysis that's done in cannabis laboratories. So with that, we'll go on to terpenes. Terpenes are basically from essential oils, and many plants and flowers in the plant kingdom produce terpenes. More than 200 different terpenes and more than 30 terpenes have been identified in cannabis plants. From a chemical definition, the terpenes are basically straight chain or cyclic hydrocarbons. They're only going to have carbon and hydrogen in their molecules. But the terpenes can be reacted by many things to add additional functional groups, usually a hydroxyl group from oxidation of the terpene, and this would be given the name terpenoid once it has a hydroxyl on it. But the generic term terpene is often used interchangeably to include the terpenoids, so we're not going to be real strict about that here tonight. We're just going to call them all terpenes, where in fact some of them are really terpenoids. Let's compare cannabinoids versus terpenes for just a second. The cannabinoids are higher in molecular weight, higher boiling point, higher vapor pressures. They're less volatile. They form less vapor, and therefore they have less olfactory detection. Basically, it means you can't smell them. Okay, but cannabis does have a very distinctive odor to it, and it's mostly due to the terpenes. Terpenes are often used in flavors and fragrances. They have lower molecular weight than the cannabinoids. They're more volatile, and they contribute to the smell of cannabis. Matter of fact, in earlier years, I used to package cannabis to train the drug detection dogs. And if you try to fool the dogs by just putting in pure THC, they won't find it. Okay, it's the smell of the terpenes that they're more accustomed to and that they're trained to detect, because they're more volatile. And if they're volatile, you can smell them. If they're not volatile, you can't smell them. So the terpenes are basically smaller components than are the cannabinoids. Now on the medicinal side of cannabis, natural and holistic medicines basically get their roots in extracting all of the chemicals from a plant source, and not just one single molecule like THC or cannabidiol. But here we're using the synergy of the cannabinoids and the terpenes to create medicinal effects. And many of the terpenes have medicinal effects in and of themselves. So some of the major terpenes are being included in a lot of the doctor's decisions for writing prescriptions and in the label claims for the laboratory analysis, so that the medical profession can take them into account during their discussions with patients. Now, strain identification is something that's becoming very, very interesting to many customers. The terpene and cannabinoid ratios will have some unique type of effect on the patient. So learning these ratios and their physiological effects on the people are becoming an interest in and of itself within the cannabis community. But there's many variables in the ratios of these cannabinoids and terpenes. The seed source, the growing conditions, how you harvest, when you harvest, even how you dry the cannabis. If you hang it upside down, if you get it too hot, if it gets too warm, some of the more volatile terpenes can actually evaporate away and be lost. And yet if you don't dry it enough, that leaves moisture in the cannabis, and that can promote mold and mildew. One of my biggest interests in this industry is the representative sample, the definition of representative sample. Differences from plant to plant, even taking the buds, the flowers from different portions of the plant versus the leaves themselves can cause differences in the terpene cannabinoid ratios. And in this industry right now, one of my pet peeves is that we have very small samples being submitted. Now, I'm working right now in 24 different states, and in the District of Columbia and in Canada, and in some locations, less than 1 gram is being submitted for the entire laboratory analysis. In some states, someplace between 1 and 5 grams, and a couple of states, 2 states now have decided that 12 grams is the magic number that is going to be submitted. If I were to do some of this type of work for the tea industry, I would request 1 kilogram of sample, and I would grind that entire sample so that I could take a small representative sample. But in this industry, that kilogram is too valuable to submit that much. So sometimes in this industry we are plagued by having too little sample to be very representative. And that's ending up causing variability and I've seen newspaper and journal articles talking about the variability in this industry. And this is one of the big reasons why, is what is a representative sample? Chemically, let's talk about the terpenes for a second. Terpenes basically start with isoprene. Isoprene is a chemical that many, many plants will produce. And in the process, Mother Nature can put a couple of these isoprene molecules together in different functions. If you put two of these isoprene units together, we get what we call the monoterpenes. And the monoterpenes might be in a straight chain, they might be cyclic, they might have a hydroxyl on them, in which case it would be a terpenoid. These are some of the common terpenes, monoterpenes that are in cannabis. Sesquiterpenes is if you have three of the isoprene units put together. There are several sesquiterpenes in cannabis also. You can even find a small amount of free isoprene in cannabis if it has not been heated too much. Because it's a smaller molecule, it will volatilize away easier and you may miss it. But there might be 30 or more different terpenes that are found in cannabis. Now, some of the things that are going to work against us is that even within the monoterpenes, all of these guys here have the same molecular formula, the same molecular weight. They are isomers of each other. So they behave very, very similarly on some instruments. Sometimes that can be problematic in trying to determine which ones they are. Monoterpenoids, linalool is very common. Limonene, if you're drinking a cola or tea or any soft drink like that, it's got limonene in it. Limonene is in many, many, many plant-based preparations that we consume. The sesquiterpenes, caryophyllene and humulene are very, very common. Caryophyllene, some people say caryophyllene, some people say caryophyllene. You say potato, I say potato. I'm not going to argue about how we pronounce it. I pronounce it caryophyllene. The sesquiterpenoids that have oxygens in them, but here are three sesquiterpenoids that are isomers of each other also. So many of these components are very, very interrelated with each other. Now, in doing extractions of cannabis, several different types of solvents have been used in history. The most common solvent is probably either methanol or ethanol. It's polar in nature and hopefully will pull polar compounds out of the plant material, but if we saw many of those terpenes had no oxygen in them, which would add to the polarity, so something that is a mixed polarity solvent can often be used. Hexane, on the other hand, which is very nonpolar, may pull some of the nonpolar components out, but have difficulties with the terpenoids that have a little bit more polarity to them. Isopropyl alcohol is a very common single solvent. There are several mixed solvents that have been used in history. One is methylene chloride and methanol, with a 9-to-1 ratio of methanol being the highest component. That's been used for many years. There's another one that I prefer. This is my preferred solvent, mixed solvent, is methanol, methylene chloride, and ethyl acetate in a ratio of 3:1:1, with methanol being the primary component. And I usually just call that solvent 3:1:1. I'll mix it up by a gallon ahead of time and leave it in that ratio, and just whatever I'm going to extract, I take out of that bottle of 3:1:1. So the extraction procedure for the terpenes, or even for the cannabinoids, might go something like this. Could take about 0.2 grams of plant material into about 20 milliliters of extraction solvent. Here I'm using 311. I might sonicate it for 10 minutes, let it, the particulates settle, or I might centrifuge it to get rid of the particulate matter. Then I can decant the liquid off, and I can inject 1 microliter of that into a GC or a GCMS, or if I take it to HPLC, I could take 10 to 25 microliters for doing the cannabinoid analysis. Or there's another procedure here that works very, very well for the terpenes, and that's called headspace. In headspace, I could take about the same amount of plant material, about 0.2 grams, and put it directly into a headspace vial and seal it up, and that's it. For headspace, we might use equilibrium headspace extraction for volatiles, and it can go by a couple of different names in the literature. One is called total vaporization technique, or TVT, or the full evaporation technique, called FET, F-E-T. And it's a very quick, easy, solvent-free extraction of the key word here is volatiles. Things that, given a certain amount of temperature, these components will go up into the vapor phase, and then we'll be able to inject it into a gas chromatograph for analysis. Again, taking about 0.2 grams of sample of the plant material, or taking oil extract from hash oil or some extract, seal it in the vial, heat it to about 140 degrees for 30 minutes in an autosampler, and the autosampler would inject the vapor directly to the GC column. So let's look at the terpene concentrations in cannabis for a second, so that we can see what amounts we're working with. Very common terpenes in cannabis are caryophyllene, pinene, myrcene, and humulene. Caryophyllene often in the 10 to 15 milligram per gram range, which is about 1 to 1.5% of the weight of the plant material. The total terpenes usually are about 20 to 35 milligrams, or 2 to 3.5% total weight. Some of the smaller terpenes might be in the concentration of about 0.2%. So let's use the 0.2% to do some simple math. If we took 0.2 grams of plant material and it has 0.2% of any given terpene in it, and we do the math of 200 milligrams times 0.2%, would give us about 0.4 milligrams of that terpene, or about 400 micrograms of that terpene that's in our sample. If we diluted this sample into liquid, we'd have that 400 micrograms. If we diluted that into 20 mils, that would give us 20 micrograms per mil, or 20 nanograms per microliter. So if we were to inject 1 microliter of this solution into a chromatograph, that should put about 20 nanograms into the injector, and at that point we would either be able to work split or splitless, and we should still be able to see that amount of terpene without too much difficulty. But we are diluting the sample a great deal, more than 1 to 10,000 in that solution. So there's a great deal of sample that we're missing, that is not available for detection. You can get more sensitivity by using splitless injection. If we do it by headspace, using total vaporization or full evaporation technique, we put the same amount in the headspace vial. We'll have about 500 micrograms of that terpene in a vial. And the amount of the vapor that we would inject, we might only get about 1/400th of the volume of a headspace vial that actually gets injected. But that's still going to give us about 1 microgram. It's 1,000 nanograms. 1,000 nanograms is a lot of sample. Okay, so that's more than 40-fold increase in sensitivity versus a liquid injection. And it's a very simple, quick, easy extraction, less dilution effect, less sample handling, less preparation. So now let's get to some chromatograms here, and let's talk about the detector of choice for terpenes. The bottom chromatogram is a GC chromatogram of about 29, I think, terpenes. And if this was done by flame ionization detector, then the retention time is the only variable that we have in order to identify the identity of a particular component. Now, there's a couple of peaks in there where the resolution is okay, but it's not perfect. Okay, so the retention time has to be very exact in order to make certain that we're talking about the right component. But if we use a mass spectrometer, then we can get not only the retention time of these chromatographic peaks, but we can get the mass spectrum of each peak also to positively confirm which terpene this is that we're reporting. We have two different terpenes here on the spectra here, and they are very similar components. They are in fact isomers of each other, but we do have differences enough that we can tell the difference in their mass spectrum. As far as I'm concerned, coming from the law enforcement community that I came out of, this is legally defensible identification. I don't want to take have any problems with misidentifying a component that could be used in a person's prescription. Some states are actually demanding that the analysis be done by single quadrupole mass spectrometer so that the components can be identified by a mass spectrum search according to the National Institute of Standards and Technologies. This particular one is showing me that this was beta-myrcene, and I know of at least 2 states that have written that into their laws now in order to make certain that a NIST search is included. Now here's a cannabinoids and terpenes from a real-life cannabis sample. This is a liquid injection. And if we look at the elution times, we'll see that the cannabinoids are retained longer. They come out late in the chromatogram, and the terpenes come out in the first 18 minutes of this long 37-minute chromatogram. So the terpenes, being very much lighter, are well separated from the cannabinoids. But if we make a liquid injection, we have to get rid of all of these heavier cannabinoids before we can make another injection. So that takes us more time and hampers our throughput. But there's ways around that. We'll talk about that. So these terpenes are coming out in the first 18 minutes. It says no terpenes in the first 10 minutes, right? So all of the terpenes come out from about 10 minutes out to about 18 minutes, and the cannabinoids would come out after that. Okay, so there's a great big empty section here of the chromatogram, but if we speed all these terpenes up in order to come out sooner, we're going to hamper some of the resolution of some of these critical pairs in there. Okay, so if we expand that a little bit larger, here we have a critical pair here that might be compromised if we were to speed this analysis up too much. Okay. Enter yet another analysis that's often done in the cannabis laboratory, and that's the residual solvents. So here is a partial list. We're adding to that list every time I turn around with different solvents that might be used to extract cannabinoids from plant material. Carbon dioxide is the most preferred, but butane is probably the most common. And if you're talking about a butane being used for extraction, they are not using pure 100%, not even 99.99% butane. This is not reagent grade butane. This is technical grade butane at the very best. And in that, there'll be some hexane, benzene, toluene, xylenes, heptane, octane, all sorts of other things. The butane itself does not hurt anybody very much in a cannabis extract. It's all these other things, especially these aromatics of the benzene and the toluene and xylenes. Let's see, let's go on here. Residual solvents, these are residual solvents that are done by Headspace GCMS. And they are out in the first 4 or 5 minutes of the chromatogram. So here's a chromatogram showing residual solvents and the terpenes in the same injection so that you can get more done with one injection and knock off both the terpenes and the residual solvents by one injection. Now, the most common column used for terpenes and pesticides and cannabinoids is a 5% diphenyl, 95% dimethyl silicon. But that's not going to do much for the residual solvents at all. So my preferred column for this is the 30-meter column, which is a 1.4 micron thick film of a 624 stationary phase that has SIL MS on it. That SIL is extremely important. So that gives it more temperature stability to be able to allow you to get up to the high enough temperatures to get the terpenes off. That raises the temperature from about 240 up to about 320 degrees for the maximum temperature of that column. The preferred analytical conditions that I use like this, again, that SIL column is what I prefer. In order to get full resolution of butane and propane, you have to get fairly cold. And not every GC will have a good time for a good, easy way to get down there. Okay, so this is the type of temperature program that I might use. Okay, now the terpenes and the cannabinoids in a liquid injection, we've seen that chromatogram before. But here's something that we can do in the laboratory to get rid of the late eluting cannabinoids in order to save time in the chromatography. We can actually turn the carrier gas around and make it flow backwards. Okay, whereas this might be one chromatogram, these aren't cannabinoids, but this is one typical chromatogram, and if I chose only to look up to there, I can save time. If I chose only to look up to here, I could save time. Okay, so now I could have the terpenes and the cannabinoids back flushed, and here we have everything including the cannabinoids. Here we have the same sample without looking at the cannabinoids. And I think this is my last slide, column switching in a single GC, being able to have the headspace set up on one injector of a gas chromatograph with a terpene column and a second injector meant for liquid injections to a pesticide column, and depending on which method you load as to which injection actually goes to the mass spectrometer. That can prevent you from having to purchase 2 or 3 instruments to do the analyses. This way you can do a lot more in one analysis. That's all we're going to talk about terpenes. I will take this opportunity to tell you that I am going to be live at a Portland cannabis seminar on October 12th at the Holiday Inn, Portland Airport. I'm also giving talks in Denver, Los Angeles, San Francisco, Washington, D.C. I don't know the dates of some of those others. Nobody ever tells me until it's time to go and get on an airplane. But if you wanted to go to the Portland facility, they will be talking about more issues on cannabis. And you can use this email right here, tombrown@perkinelmer.com, if you're interested. Or if you want to talk to me anytime, there's my email at timothy.ruppel@perkinelmer.com. How do we do for time? Did I go over?
You went over by 2 minutes, so you're doing pretty good, Tim.
2 minutes. That's not bad for me.
Thank you so much.
Can I take any questions from you?
That was pretty technical. I think our own Dr. Roger Volker probably got more out of that than most in the audience. But does anyone have any questions for Tim Ruppel while we have him on the line? Show of hands.
Yes, I had a question about polyterpenes, where the cannabinoids and the terpenes combine and form polyterpenes. Could you describe that process and how it happens, please?
I am not qualified to talk as to how the morphosis works from one to another. I can tell you how to analyze for them and tell what they are there, and if they do become larger terpenes, then they're no longer volatile enough to go into headspace, and now I need to use a liquid injection in order to determine what they are and how much of that is actually going on. So I'm afraid I would have to defer to somebody who has more botanical experience in botanical chemistry than I do.
Okay, we have one more in the back over here.
Hey there, since you're a specialist on the residual solvents, I was just wondering if you happen to know if any of those solvents form azeotropes with compounds in the resin, such that they kind of elute at the same time.
We can, yes. Very small concentrations we actually find in the plant material itself. That if you were to do a residual solvent analysis on the bare plant material, you're talking about part per million levels that you might find in the plant material, whereas anything in the extraction community is going to be in the percent level, much, much higher. So the amount of solvent that the plant material itself is supplying is very minimal and negligible.
I don't think that answers my question. I was asking if any of the resin compounds form azeotropes with any of the solvents that are ever used.
Oh, okay. I see. That's what you're saying. I would not doubt it. Okay. Now, methanol is probably the most common solvent that's used. But methanol is probably one of the most reactive chemicals that's in that list also. Things like ethyl acetate and methylene chloride will probably not react as much as with the methanol. But methanol itself is really quite corrosive and can react with many things. So I've never read anything where the azeotropes that could be formed are in much high enough concentration to be of any concern.
Did that answer your question? Okay, thank you. Do we have any other questions for Dr. Ruppel? Any other hands? Okay, I think that does it for our discussion with Dr. Ruppel from PerkinElmer. Thank you so much for taking the time tonight. Tim Ruppel from PerkinElmer, remoting in all the way from Chicago. All right, Tim, we'll let you go. Again, thank you.
Okay, I will sign off now. Bye.
Enjoy the rest of your trip.